And then I'm going to share my screen with you. All right, so here we are. You guys, this is 13.1. What color do I want to use? Probably not red. Red's a little harsh. Let's do purple. Okay, purple. So this is 13.1, and it's called antiderivatives. So antiderivatives, guys, so you can see the word derivatives, which we know, and anti implies that we're going to do the opposite of taking the derivative. And that's exactly what we're going to do. So you guys, I want to start with notation. What you're going to see today is this symbol for antiderivatives. Also, guys, so taking the antiderivative is one way. We also call it integration. So I'm going to kind of go back and forth. Integration is the act of taking or finding an antiderivative. So you guys, the notation is this kind of swirly line. Now I've ruined it. Kind of like an S, if you were to take an S and then stretch it, you know, from top and bottom. Kind of like a really tall, skinny S, I guess. But when you see it, there's going to be a function in it, you guys. So let's say you have a function in here. This is, I want to take the antiderivative of the function. And you guys, it's always going to have this dx as part of it. And the dx right now is just notation for us. It says we're going to take the antiderivative with respect to x. Just like remember when we did the derivatives, we didn't really use it anything other than notation when we had dy dx until we got to implicit, and then we did have to actually use it in operations. This is kind of the same way. You guys, dx is just a notation right now, but as we move on into more sections of chapter 13, we will end up having to use it in operations. So we're going to always have it there. For right now, it's not going to really mean much other than with respect to x, but later we will use it. So we want to make sure that we always have it. So this notation here says I want to take the antiderivative of a function with respect to x. So we need to now talk about how to take an antiderivative. So you guys, if I start with a function f of x equals 2x, and I want to take the antiderivative of this 2x with respect to x. My answer, and I'm going to give you the answer, then I'm going to show you how I got there. You guys, my answer is actually going to be x squared. There is going to be another value here we're going to talk about, but the main part of the answer is x squared. So how did I get from 2x to x squared? Well, you guys, I took the derivative backwards. Can you see that? So can you see that if we had started with x squared, you take the derivative and you get the derivative is 2x. Can you see now that we're starting with the derivative and getting out like the original function that derivative came from? So you guys, we're going backwards. Now I said that there is another term in our answer that I need to talk about. So you guys, you have 2x, you guys, as a derivative. Where did it come from? Well, obviously it came from x squared, because you take the derivative, you get 2x. But what if f of x had been x squared plus 5? When you take the derivative of that, don't you also just get 2x? And what if I had had f of x equals x squared minus 100? When you take the derivative of that, don't you also just get 2x? So you guys, there's an infinite number of possibilities, you guys. So if I'm telling you that the derivative of a function is 2x, and I want you to find the original function that came from, sure, it's going to be x squared, but there could have been any other constant with it, and your derivative still would have been 2x. So you guys, we don't know if there was a constant on it or not, you guys. So when you already have the derivative and you're going back to an original function, what we do in our answer is we write a plus c, and c just stands for any constant. It could be nothing. C could be 0, and your answer could just be x squared. But because we don't know what the original function had in it, we say plus any constant. X squared plus a constant, when you take the derivative, will always equal this 2x. So you're going to notice that plus c a lot, and you'll get used to it because it's going to be in all of our answers today. So let's look at another example. You guys, I want to take the antiderivative of, what if I have 5x to the 4th? So you think, and you read this and say, okay, I'm taking the antiderivative, which means I'm treating this like it's a derivative. And I want to find out what function that came from. Well, you guys, with some thinking, you can find out that that came from x to the 5th, and then I'll put plus c because it could have been x to the 5th plus 7. It could have been x to the 5th minus 25, and it still would have ended up as 5x to the 4th. And you guys, the reason, what happened?
What just happened?
Guys, I lost my, where'd it go? Woo, that was scary. Okay, you guys, so the reason why I got x to the 5th was because I was thinking about, okay, how would I have gotten 5x to the 4th from the original? I'm thinking the power rule, right? I'm thinking, okay, so the 5, look, the 5 would have come down in front, and then I would have taken a power away. And I've done derivatives enough to kind of be familiar with what they look like. So you guys, I just used my brain here to think, oh, that had to have been x to the 5th plus some constant, possibly. But you guys, we're not going to just be thinking, and critical thinking and using our brains in that certain way on all of these, because these are going to get more complicated, and it's going to be harder to just switch your brain into backwards mode and just think about what it would be every time. You guys, we actually have rules that will get us there every time, so we don't just have to think really hard. I don't know how else to say that. These aren't puzzles to solve, right? I mean, they kind of are, but we have rules that help us. So you guys, while this is true, we have a power rule for antiderivatives that will help us. We don't want to just do trial and error. So you guys, the power rule for antiderivatives is exactly opposite of the power rule for derivatives. And that should make sense, right? So remember, in a derivative, we took the power, we bring it down in front with multiplication, then we take one away. So for example, if you had x to the 5th, what would you do? You would take this 5, you put it down in front by multiplying, and then you take a power away. So we're very good at that. Let's think about how to write it backwards in a general form. So let's say you have a function f of x equals, let's just use x to the n power. And you want to take the antiderivative of that, which would equate to being the antiderivative of x to the n. What you're going to get is 1 over n plus 1 times x to the n plus 1. Plus c, of course, because we always have a plus c in these general antiderivatives. So you guys, let's talk about why it is what it is. So remember, in the going the derivative direction, we take the power that's up here and we bring it down with multiplication. So we bring a number in the front with multiplication. Can you see why now I have a 1 over, you guys? Because I'm bringing it in the front with the opposite of multiplication. I'm bringing it down in front with division. And am I subtracting 1 from my power like I did in the derivative? No, I'm adding 1 to my power. So you guys, this 1 over n plus 1, x to the n plus 1, is basically the exact opposite thing of your derivative power rule. But we can use it to find our answers always. So you guys, let's use that. So this one we just did with, thinking, trial and error, what could this be? Now we're going to use the rule so we don't have to do that anymore. So in this example, I want you to take the antiderivative of x to the 7th. And I want us to use the power rule. So you guys, 7, that's your n. So your n is always just the power you're given. It says I do 1 over n plus 1. So 1 over 7 plus 1 is 8. And then x to the 8th plus c. And you guys, that's it. If you're worried about it, you can always take the derivative of this and make sure you get back to what you started with here. But we get 1 over 8 times x to the 8th. If I have in here just x cubed, well, my 3 is my n. So you guys, n plus 1 would be 4. That's the number I'm going to be working with. Notice n plus 1 goes here and here. So n plus 1 is 4. So I end up with 1 over 4 x to the 4th. Again, you can check that if you want. You will, if you take the derivative of this, you will get x cubed. What about this one? I want to take the antiderivative of x to the negative 4 with respect to x, of course. Well, you guys, even though it's a negative exponent, our power rule still holds, just like it did with derivatives. You guys, so let's think, or that's not what that, okay. You guys, your n is negative 4. So what's your n plus 1? That'd be negative 3. So negative 3 is the number I'm going to put in the front and on the power. So you guys, remember it's 1 over. So 1 over negative 3, x to the negative 3. And that's it, guys. So negative exponents, not very different. What about roots? You guys, what if I got the square root of x? Well, just like the power rule for derivatives, if I'm using a power rule, I need to write this as a power. So you guys, the first thing I would do is write it as a power. Instead of writing square root x, remember I can write x to the 1/2. So it looks like my n is 1/2. What would your n plus 1 be? Well, 1/2 plus 2/2 is 3/2. So you guys, 3/2 is my n plus 1. So when I write this out, it's 1 over n plus 1. So I'm going to have a complex fraction here for a minute. I have 1 over 3/2, and then it'll be x to the 3/2 plus c. You guys, what do I do here? 1 over 3/2, what happens? Well, the 3/2 is just going to flip over. Think about it. How do you divide by a fraction? Don't you just flip and multiply? So you guys, when you have 1 over a fraction, it's really just the reciprocal that's happening. So when I see 1 over 3/2, I know I'm just going to flip it over. It's going to be 2/3 x to the 3/2 plus c. Make sure that while you flip this number over, this one doesn't get flipped. This is just the power. It's what it is. But you guys, so I did a root and the power rule worked. It was fine. What about this one? So you guys, when I have x on the bottom, let's make it 1 over x squared. You guys, now I have x on the bottom. What do you think I would do first before I started taking the antiderivative? What did I do the other direction? Didn't I rewrite it as a negative power? You guys, I would write this as x to the negative 2. And then I would continue on using my power rule where n is negative 2, so n plus 1 is negative 1. What's the rule? It says 1 over n plus 1, so 1 over negative 1 times x to the n plus 1 plus c. You guys, as far as simplifying this one goes, I would just call this negative x to the negative 1. So it seems pretty straightforward. You guys, we have the rule. You don't have to memorize it right now. You'll get there. Just like, when's the last time you actually had to write down the power rule for derivatives, right? At first it was like, okay, I have to remember this, I have to reference, and then all of a sudden it was second nature. It's going to be the same with this if you practice it. 1 over n plus 1, x to the n plus 1 is going to become just something that's in your head, and it's going to be easier, but you can always reference it in the meantime. So let's see, what about this one? What if I just want to take the antiderivative of 5 with respect to x? This one can give us trouble because when you see a constant, your first thought is it goes away. Because when we take the derivative, it does go away. But you guys remember, we're going backwards. So this 5 is not going to go away. I want you to think about a constant, 5 in this case, as 5x to the 0. You guys remember, you can write any constant number that way because x to the 0 is just 1. So for example, if I just had a 3, I could always write it as 3x to the 0. Or if I had a negative 25, I could write it as negative 25x to the 0. So you guys, if I write it this way and I say that my power on x is 0, my n plus 1 would be 1. And let's use the power rule for antiderivatives to find my answer. Hold on. So first of all, let's talk about the 5. In this case, the way I have it written, isn't 5 just a coefficient on my x term? So you guys, to know how to do constants, you do need to know that coefficients come along in antiderivatives the same way they did in derivatives. So, you know, every time I took a derivative, if it had a coefficient in the front, I just brought it along. It's going to come along just the same way. You guys, so I have a 5 that comes along, and then I'm going to take care of this x to the 0. So it's 1 over n plus 1. Remember, our n plus 1 here is just 1. And then x to the n plus 1. So isn't that 5 with a bunch of 1s multiplied by it? Or a1 multiplied by it and then x to the first. I said that in the weirdest way that I could. So you guys, this is 5 times 1 times x to the first. So we just get 5x. So what I want you to think of, because sometimes you don't want to have to put in x to the 0 when it's not really there and use the power rule. What I want you to think of instead is if you have a constant and you're taking the antiderivative, all that's going to happen is you're going to add an x to it. Because think about going the other way. If you started with 5x and you took the derivative, you always just get 5, right? The x just goes away. If you started with negative 50x, what's the derivative of that? Well, it's negative 50. So if you're going backwards, you guys, if you have a constant, when you take the antiderivative, all that happens is it gets an x. You can see the power rule happening behind that. So, you know why it's happening, but that's what is happening. Let's do some more on that coefficient business. Remember I said on this one, the coefficient just comes along, and it absolutely does. So what if I had 7x to the 8th dx? Well, let's take the antiderivative using the fact that coefficients are still just going to come along. You guys, I would have a 7, and then I would do the power rule here on the x to the 8th. If n is 8, then n plus 1 equals 9. So you guys, that's the number that's going to be in my answer. I'm going to have 1 over 9 x to the 9th plus c. Let me write the power rule one more time because it's not on our screen right now. As far as simplifying this one goes, you could write that as 7 over 9 x to the 9th plus c. That's how I would write it. So what if I've got x to the 5th over 8 dx? So sometimes I need to be able to recognize where a coefficient is. You guys, this x in the fraction like it is, couldn't I just write this as 1/8 times x to the 5th. Isn't that the same? You guys, you can pull that fraction out. Remember, there's a 1 right here. Pull out the number from the x term if you've got something like this. Don't let it fool you. It's just a coefficient. And you guys, then I would continue with the problem here. I don't know what's happening. There we go. So when I got my answer, this coefficient 1/8 would just come down. If my power right now is 5, then the n plus 1 that I'm working with in my answer is a 6. And it's 1 over 6, x to the 6 plus c. Then you guys, you can just multiply those two fractions together and you'll get 1 over 48, x to the 6 plus c. So lots of different combinations that you could see, a lot of different ways they're going to write stuff, but so far we've just been using the power rule. Now I want to show you where the power rule breaks down on us. So you guys, what if I want to take the derivative of 1 over x? Just 1 over x to the first down here. Well, normally what I would do here is I would rewrite this with a negative power so I can take the power rule, right? So let's do that. So you could rewrite that as x to the -1 power. Now, if I'm going to use the power rule on this, then my n is -1. What's my n plus 1? -1 plus 1 is 0. So 0 is the number I'm working with in my answer. So what is the power rule? I lost it again, you guys. 1 over n plus 1, x to the n plus 1. So if n plus 1 is 0, I'm looking at 1 over 0, x to the 0 plus c. And you guys, there's a problem. You guys, there's not a problem here. X to the 0 is just 1. But 1 over 0 is not a thing the last time I checked, and it will never be a thing. So this is a problem. So it looks like the power rule has broken down on us when x is raised to the -1 power, or in other words, when we have 1 over x. But you guys, this might make a little sense because remember, think working backwards. What I'm telling you is that 1 over x is the derivative of something, and I want you to find that something. Well, what is 1 over x the derivative of? I should know. You guys, if we started with the natural log of x and I take the derivative, what do I get? Don't I get 1 over x? So you guys, the power rule isn't going to get me backwards starting here and getting to here, right? So that's why the power rule didn't work here, because this isn't a power problem. This is actually a natural log. The only thing is, when you're taking the derivative, they give you the natural log, and then you just know what the derivative is. You don't see the natural log here, but you have to know that when you take the antiderivative, that's what it's going to be. So you guys, this does not make sense. So instead I think, oh, okay, if my derivative is 1 over x, where did that come from? Well, it had to come from the natural log. And you guys, it is that simple, but with a little bit of complication, of course, because why would there not be? When you're taking the antiderivative and your answer is natural log, whatever is in the natural log has to be put in absolute values. And you might wonder, why have we never had absolute values on natural logs before? Well, I will do my best to explain it. So let's think about this problem over here. This is what we're used to. They give you the natural log statement in the question, and then you took the derivative, you got 1 over x. You guys, if a natural log statement is given to you, especially if it's part of a function, so if it says like f of x equals natural log x, that assumes that x is positive. You can absolutely look at this and assume that x is positive because they're the ones who wrote the question. They're saying that this is a defined situation. And if you're wondering why it matters if x is positive, if you're not up to speed on the logs, you guys, you can't take the log of a negative number. So for example, the natural log of -3 doesn't exist because you can't have a negative number here. It just doesn't exist. So That's why when it gives you this part, well, obviously x has to be positive, even though it doesn't ever say, hey, we're restricting x, it has to be positive. Because they wrote it in a function notation, they gave it to you as a problem, you can assume that it's positive. And when you take the derivative, you just write 1 over x. And when x is on the bottom of a fraction, notice it doesn't matter if it's positive or negative. So we just never had to think about the sign of x being a possible issue. But guys, did they give us the natural log in this equation? They didn't. We are the ones who put it in there. So when you just have 1 over x, 1 over x is defined whether x is positive or negative. So there's nothing in this statement saying that my function is 1 over x that restricts x and says it has to be positive. So because it's not restricted in what's given, when I change it into a natural log function, I cannot assume that x is only positive. So to take care of it, I use absolute values. So basically, when you introduce a natural log into the problem, you have to put the argument in absolute values. And if that made sense on why, then that's great. If it didn't, that's okay. You just make sure when you write a natural log as an answer, you put absolute values. Because it does matter, you guys. It is important. So for example, so obviously when we just have 1 over x, our answer for the antiderivative is the natural log of absolute value x. What would it look like if there's a coefficient in there? Maybe I would have 4 over x. Could you separate the 4 from the 1 over x? Yeah, you can bring the 4 out. See that this is really a coefficient of 4 on the 1 over x. How would I take the antiderivative? Well, the coefficient would come along. Then I would take the antiderivative of the 1 over x, which I know is natural log absolute value of x, and then a plus c. So you guys, if you have x to the first on the bottom, it really doesn't matter what's on top because you can take that out as a coefficient. Your answer is going to be a natural log. Now, what if you had the antiderivative of 1 over x squared? Is this going to be a natural log? It's not, right? Because remember, you can just write that as x to the negative 2 and use the power rule, and that would work. You guys, it's only 1 over x to the first, or 4 over x to the first, or anything where there's an x to the first on the bottom is gonna come out as a natural log. Because when we went the other direction, every time we had a natural log, we put an x to the first on the bottom. So you guys, what I want to do next is exponential. You guys, I want to take the antiderivative of e to the x. Remember how to take the derivative of e to the x. So let's recall again. If you started with e to the x and then you wanted to take the derivative of that, didn't we just get the exact same thing? So what do you think is going to happen when we work backwards? You're still going to get the exact same thing. It hasn't changed. So you guys, the antiderivative of e to the x is e to the x plus c, of course. But it really is that simple, just like it was with taking the derivative. Now, when it's more than just an x in the power, we have to think a little harder on it. You guys, so for example, if I've got e to the 3x dx. Now, for some reason, the e to the x problems are really hard to break the habit of taking the derivative. When you see e to the 3x, what do you want to do? You want to bring that 3 down, right? You want to call this 3e to the 3x because that's what happens when you take the derivative. And I'll even write that over here because it'll help us figure out what we're going to do. If you started with e to the 3x and you took the derivative, using some chain rule and what we know about exponentials, you would end up getting an answer of 3e to the 3x. So what happens is whatever this coefficient is up here with the x, it comes down with multiplication. So what do you think is going to happen to it when we go backwards? You guys, first of all, note that the e to the 3x part actually just came down as is, because remember, the exponential term never actually changes. It's just what's around it. So I'm going to bring down the e to the 3x as is. But you guys, instead of bringing this 3 down with multiplication, I'm going to bring it down with division. So I did the opposite thing, and that's it. So I get 1/3 e to the 3x, and that's it, guys. So whatever this number is, just put 1 over that. And notice, don't get it mixed up with the power rule. I didn't add 1 to it. You guys, I left it exactly the same. I just did 1 over that number, and then I put my exponential term as is. So let's look at another one like that. So if I have the antiderivative of e to the 7x dx, what's that going to turn into? Well, I'm going to have the e to the 7x, but what's this 7 going to do? It's going to come down in the front, but be divided. So it's going to be 1 over 7, e to the 7x plus c. Let's put a coefficient on it. You guys, what if I have 5 e to the 5x dx? Well, coefficient rules say that that just comes along. So I bring the 5 over. But this 5 here needs to come in front with division. So I'm going to end up with the 5 that was already there times a 1 over 5 e to the 5x. And then what happens with the 5 and the 1/5? Well, they just go away. So you end up with just e to the 5x. So you guys, these are the rules you're going to use as you do your homework in 13.1. Sorry, I'm moving it too much. So we have the exponential, we have the natural log, then we have the basic power rule. You know, coefficients work the same way. They just come along anytime you see them there. Constants, make sure you don't disappear those constants anymore. If you have a constant, it just gets an x. So 4 turns into 4x, 3 turns into 3x. You get that pattern. But so what I encourage you to do, so I'm going to be opening your homework here in a second for 13.1, and it's just practice. It looks a lot like these do. One thing that you're going to see, so for example, you're going to see functions with multiple terms. So let me just make sure you know, and you probably would figure it out. So like, what if I had x squared minus 3x plus 5 or something like this? You guys, if you have multiple terms in here, just like derivatives, you can take the antiderivative of each term separately and then just put a plus c on the end. So don't let that throw you. You're just going to be doing each term. Sometimes your homework has multiple terms, so I want to put that out there. So for example, what would this one be? You guys, your n would be 2, so your n plus 1 would be 3. You'd have 1/3. Why? 1/3 x cubed minus, what about this 3x to the first? Well, if your power is 1, then your n plus 1 that you're going to work with is 2. So your coefficient 3 would come down. Then you'd have 1 over 2x squared. And then what about the plus 5? What did we just say about a constant? Well, it's just going to get an x. So it'd be plus 5x. So I did the power rule on each of these separately, just like you would if you were taking the derivative. But with that being said, you guys, your homework's just practice on all these kinds of different antiderivatives. While it's not due till Sunday night, you know, I would encourage you to look at it before Friday, because we're going to be doing some other things and you want to be at least a little bit comfortable with going this direction before we get to the next part. And also on Friday, I will actually be on campus on Friday. I I have a meeting, so I will be up there anyway. So I'm going to be on campus for our classes. So if you're an in-person student, you really like being in person, this is a good chance to do that. Definitely not a requirement, of course. Just because I have to be on campus doesn't mean you do. But you know, if you've been really missing that, this is a good time because I will be there for class on Friday. So I want you to look at your homework, you know, try to get started on it. I will be on campus in our classroom. I know it's been a while, but our classroom is 103, I'm pretty sure. I could be wrong. I think it's 103. It's been a while, huh? But I will be there on Friday if you want to come in person class. And other than that, that's all I got for you today. So I'll either see you on Zoom or in person on Friday.